Hello, everyone. Thank you for joining me today as we look into one of the most fascinating and transformative topics of the digital age: cryptography in blockchain. Cryptography is the backbone of blockchain technology, ensuring its security, integrity, and trustworthiness. By the end of this seminar, you will be able to understand how cryptography enables blockchain to revolutionize industries like finance, healthcare, and supply chain management. So let's get started. First, let's look into a quick let's quickly look into what blockchain is. A blockchain is a decentralized distributed ledger system that records transactions across multiple nodes in a network. It operates without a central authority, which means no single entity controls the data. For this system to function securely, it relies heavily on cryptographic techniques. These techniques ensure three key aspects: confidentiality, that is, only authorized parties can access the data; integrity, transactions cannot be altered once recorded; and authenticity, the identity of parties involved is verified. So let's now look deeper into how cryptography makes all this possible. So at the core of blockchain lies cryptographic hashing. A hash function takes an input and converts it into a fixed length string of characters, which represents the data uniquely. In blockchain, each block contains a hash of the previous block, forming a secure chain. Any change in a block's data would alter its hash, breaking the chain and or alerting the network to tampering. The most common hashing algorithm used in blockchain is SHA-256. Here is why it is so effective. First, it has a fixed output. Regardless of the input size, the output is always 256 bits long. Second, deterministic. The same input will always produce the same hash. Third, irreversible. It's computationally infeasible to reverse engineer the original data from the hash. And fourth, collision resistant. No two different inputs will produce the same hash. For example, in Bitcoin, the hash of each block ensures the integrity of all previous transactions, creating a secure ledger. Moving on, let's explore public key cryptography, or also known as asymmetric cryptography. It's a critical component of blockchain used to create wallets, sign transactions, and verify identities. This system involves two keys: private key, which is known only to the owner and it's used to sign transactions, and the public key, which is shared openly and is used to verify those signatures. Here's how it works in blockchain. When you create a wallet, it generates a private key and a corresponding public key. The public key is then hashed to create your wallet address, which is shared for receiving funds. When you send funds, your private key signs the transaction, proving that it is coming from you. The cryptographic algorithms behind this, like RSA or ECC, ensure that it's practically impossible for anyone to guess your private key, even with access to your public key. Another essential cryptographic concept in blockchain is digital signatures. These are used to authenticate transactions and ensure they haven't been tampered with. Here is how they work. A sender uses their private key to generate a signature for a transaction. The network nodes use the sender's public key to verify the signature. Digital signatures in blockchain ensure two things. Number one, authentication. The transaction is genuinely from the owner of the private key, can be verified. Number two, integrity. That the transaction data has not been altered. This process is what enables trustless systems like Bitcoin and Ethereum, where participants don't need to know or trust each other to conduct secure transactions. Let's now discuss consensus mechanisms, the protocols blockchain networks use to agree on the validity of transactions. Cryptography plays a major role in two popular mechanisms. One, proof of work. Miners compete to solve a cryptographic puzzle by finding a hash that meets specific criteria. The first miner to solve the puzzle adds the block to the blockchain. This process requires significant computational power, making it secure against tampering. Second is proof of stake. In this, participants stake their cryptocurrency to validate transactions. Validators are chosen based on factors like the amount staked and randomness. Proof of stake uses cryptography to ensure fairness and prevent manipulation. Both of these mechanisms rely on cryptographic techniques to maintain the blockchain's integrity and security. Blockchain is not just about recording transactions. It also powers smart contracts or self-executing contracts with terms written into code. Cryptography ensures the security of these contracts by verifying the identities of participants, encrypting sensitive data within the contract, using digital signatures to trigger actions when conditions are met. For instance, in an insurance smart contract, cryptographic algorithms can verify claims automatically, ensuring transparency and efficiency. While cryptography makes blockchain secure, it's not without its own challenges. One is quantum computing. The rise of quantum computers could potentially break existing cryptographic algorithms like RSA. To address this, researchers are developing post quantum cryptography. And the second is scalability. Complex cryptographic operations can slow down blockchain networks. Efforts like zero knowledge proofs aim to solve this. Despite these challenges, cryptography continues to evolve, enabling blockchain to expand its applications from decentralized finance to healthcare and beyond. In conclusion, cryptography is the foundation of blockchain, enabling its security, transparency, and decentralized nature. Whether it's hashing, digital signatures, or public key cryptography, these techniques empower blockchain to revolutionize industries. I hope this seminar has given you a deeper appreciation of the role cryptography plays in blockchain. So until we meet next time with another new topic, stay safe.